Oh, welcome back again, folks. This time we're going to talk about stellar evolution. So we've talked about frequencies and wavelengths, and talked about absorption and emission spectra that stars produce. Now we're going to talk about the life cycle of stars. So to start out, the background I have here is a beautiful image of part of the Orion Nebula, also known as M42. It's a beautiful nebula in, well, the Orion's tunic, essentially. And it's great to view with binoculars. But within that nebula are, as just an example, it's also known as what's called an H2 region, a star-forming region. Within that nebula are what we call protostars. And these are all examples of stars in various stages of development. As the cloud begins to condense, eventually the stars will get to a point where fusion ignites, and some of these are closer than others. Like that one's pretty close to fusion being igniting. That's essentially when you have a full-fledged star. When fusion ignites, and then you then end up on the main sequence. Let's call it the main sequence. So fusion ignition is I love this. This is a beautiful artist's conception of what it might look like for a star to actually go from protostar to star. The ignition of hydrogen fusion. So hydrogen fusion is, again, if you're not familiar with that, it's the process of four hydrogen atoms fusing to form a helium atom. So the product of hydrogen fusion is not only helium, but it's also energy and neutrinos. It's a pretty powerful process. If we ever master it here on Earth, and contain it, we'll be able to have unlimited power, essentially. So if a star is born with a very little mass, we call it a white, they can be born as a white dwarf or a dwarf star, and it can, this is what we call a main sequence star with low mass, and it lives for a very long time, billions of years. In fact, any dwarf stars that are born at the beginning of the universe are still dwarf stars. They've not died yet. So, yep, still burning billions of years later, until finally it basically fizzles out. Now that's one way for a white dwarf to die. There is one type of supernova it's not a very dramatic supernova, type 2, I believe, that can happen with white dwarfs. But for the most part, the end result is a black dwarf, which is kind of like Jupiter. Jupiter is kind of an example of a black dwarf. Jupiter is a planet that essentially is a star that never got going. It could be seen as. All right, well, if you're back at the ignition stage, and let's say you're not a low-mass star, but let's say you have a lot more mass, a lot more gas involved, and you become a medium-mass star like our sun. Well, then you move up on the main sequence a little bit, right offhand, and your life and you don't live as long, about 10 billion years or so. Eventually, you're going to reach the red giant phase, and as you all discovered at the toilet paper lab, when the sun becomes a red giant, Mars will be lucky if it's not within the sun. So Earth will no longer exist at that point. And that's about 4 billion years from now, so you don't have to worry. You'll be long gone. But after that happens, eventually be, you get to the point where the star when it comes to red giant phase, it's no longer burning hydrogen. It's actually fusing helium to form carbon. It's a very similar process, just bigger atoms. But it can never get warm enough to actually ignite carbon to produce nitrogen. So what ends up happening is that the star eventually collapses in on itself and then sheds its outer layers as a planetary nebula. This is an example of a really nice planetary nebula, a very famous one. And then, oh wait, it's not quite dead yet, because it actually goes down and becomes a white dwarf, which is usually found in the center of these nebulae. And then, of course, it can last for perhaps billions of years and still be burning billions of years later and eventually die as a black dwarf. This is, of course, the predicted model. Now let's go back. Let's say you've got just ridiculous amounts of gas around you as a protostar when you form, and you're just really, really massive. You're that 10-pound baby born in the hospital. And mom had a heck of a time in labor. You just come out and everybody's just amazed at how big you are. Well, that's essentially what happens to, when you're born as a giant or a supergiant on the main sequence. You don't stay on the main sequence very long. You actually end up dying relatively quickly. So maybe about a few million years or a billion years at the most. This is an example of a blue supergiant, very, very hot star, very, very large, very bright. Eventually, you'll go out with a real bang. It's the type of supernova. This is Tycho's supernova. Remember Tycho with the gold and silver nose. And then you either go one of two ways. If you're not so massive, you're massive. I mean, you're massive, but you're not like, the most massive. Then you'll become a neutron star, also known as a pulsar. And we're going to spend a lot of time on these because they're very interesting, and you're going to get the chance to be a pulsar astronomer here in the coming weeks. But there's the or. If you're really, really massive, then you become a black hole. And those, of course, are also pretty darn cool. So pulsars and black holes are something that I like to talk about a lot, so you're going to get probably tired of it. Maybe you won't. Now, I've talked about the main sequence a lot, and then giants and dwarves and things of that nature. This is an HR diagram. You need to learn the basics here, okay? The basics are, these are, the letters here indicate a spectral class of the stars. Basically, corresponds to color. So these reddish stars are cooler. The bluish stars are hotter, essentially. So increasing temperature this way, decreasing this way. So you should, and this is in Kelvin, not Fahrenheit or Celsius. So the main thing to know is that on this axis, the x-axis of the HR diagram, it's Kelvin temperature, and it's increasing to the left, which I know is backwards, but just bear with me. That's just the way it's done, okay? Now, luminosity makes a little more sense. This is also known as brightness. Uses solar units mean in terms of sun. So a star with a luminosity of 1 would be our sun. So we actually calculate luminosity based on our own sun, and so some of these stars, obviously up here, 10 to the 5th suns. Now that is a huge star, really, really bright. Think of that Bic lighter you buy at the convenience store. When you buy it, the flame is oh so bright in the dark. But then you take the top off and you adjust it a little bit, and you go back into a dark room, and that flame is like 3 feet high. It's much, much brighter than it was because the flame is much bigger. Likewise with stars, the bigger they are, the brighter they are because they have more surface area. So the big giant stars, and even more so the supergiant stars, are really, really bright. Now, of course, the color determines temperature. So blue supergiants are obviously very hot. Red supergiants are obviously much, much cooler, even than our own sun. But this is an HR diagram. I'll give you a copy of this because you're going to need to know it. Okay? You have to know this stuff. All right, there's another version of it, a little scrunched because they wanted to focus on our sun. Our sun specifically is born right about where it says wherever one solar mass is, which is about down over here. Okay? And at some point, it's burning hydrogen, 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 hydrogen. And at some point, it nearly runs out of hydrogen fuel. It starts to fluctuate, and it becomes kind of variable and fluctuate in size. And at some point, it, bam, ignites helium, and then it eventually swells to the size of a giant. And why do stars stay at the size they're at? Because gravity is balancing. Gravity keeps the star from exploding. That contains the fusion reaction. And the fusion reaction puffs the star up. So at some point, they have to reach equilibrium between gravity and fusion. And that's called hydrostatic equilibrium. So on the main sequence, hydrostatic equilibrium is based on the temperature of hydrogen fusion. In the giant phase, it's based on the temperature of helium fusion, which is much higher than hydrogen fusion, so the stars get bigger. One more thing about the HR diagram. Sometimes I like to think of the main sequence as kind of like Middle Earth, okay? Here's a little Lord of the Rings analogy for you. Middle Earth. And I'm combining a couple fairy tales here. There's Lord of the Rings stuff. Eventually you climb up the beanstalk to find the giant. Ha ha ha. And then maybe you decide you run into the giant, you don't like him, and you decide you want to jump off the beanstalk, and then you descend down into the mines of Moria, where the dwarves are. Okay, so I will expect you to know where the main sequence on an HR diagram is, the giants, the supergiants, and the white dwarves. Likewise here, you should know roughly what's going to happen to our sun. Okay, after it goes through the giant phase and then becomes a planetary nebula, it'll become a white dwarf eventually. All right, well, that's it for that. Get more detail in class, but otherwise, have a great evening. Talk to you soon.